Hi everyone. In a lot of subjects, practice problems are considered the best way to prepare and learn concepts, be it in math, computer science, lead code, physics, chemistry, whatever. One common issue I think a lot of people face is that when you're practicing or you're in a study session, you get some problems that are so easy that they feel trivial, and others are impossibly hard. You have to pick up the answer key in a few seconds. In both cases, it doesn't feel like you're actually learning. You might get something in between where a problem is just right. It's hard enough where you're actually learning stuff, but it's not so hard it feels impossible and have no idea what to do. Formally, in learning science, this is called the zone of proximal development. Here's the idea. Take two students who know basically the exact same amount. They're in the same classroom, they're from the same background, they even have the same IQ. Give them the same bank of practice questions, they can actually learn very different amounts, purely from the order that they do those problems in. A sequence where every problem lands in the student's zone of proximal development, I'll call it ZPD, that's what optimizes learning. I don't think there's a system at scale that actually follows the ZPD principle. For example, existing ones might tag problems as easy, medium, or hard, but real difficulty depends on the student themselves and their history. If you don't personalize the difficulty, it doesn't really mean anything. That's exactly what my model, Qwen-QRec, does. I frame this as a recommendation task and use a frontier paradigm, generative retrieval. Instead of embedding or keyword search, which usually optimize for like semantic similarity, or using like an algorithm for engagement, you can train a sequential model, here a pre-trained language model, to generate the ID of a next question from a student's history. It learns both how to output real questions, real existing questions, and how to condition on a history to present a question that fits in the zone of proximal development. This is a training pipeline. The goal is to get Qwen 3 1.7 billion parameters to output the next problem a student should try, given their past ones. This is not a chatbot. It's designed to be embedded in a tutoring/practice system. I built it for 6th to 8th grade math, but with the right data and maybe a bigger model, it should generalize to any topic. First stage is to condense every question into something the model can output. We use an RQVAE via residual quantization, which turns each problem into a short 4-part code, where similar problems share a prefix. Like the broadest category might be the first number, and you get more fine-grained as you go on the code. This is trained on about 3,300 math problems from the foundational assist dataset. The main thing to watch for in this model is to make sure the codes are well distributed across the code space and making sure the codes carry some semantic meaning about what the codes actually mean. The second stage is a model that estimates the question's difficulty for a specific student. These are knowledge tracing models. They read what a student got right and wrong and predict their chance on the next problem. This most data heavy stage has over 33 million attempts split by student, like across 3 math datasets. I trained two things here. First, a reward model to score and label problems per Qwen for later fine-tuning, and then an independent evaluator for evaluating the results of Qwen downstream. This had about 0.82 AUC. The third stage is LoRa SFT on Qwen 3 with over 100,000 real student interactions and histories, teaching it to read a history and generate the next problem's code. It uses SID to text semantic alignment strategies from Mini Qwen-QRec, which I adapted with topic mastery summaries and prerequisite alignment, all built deterministically, not synthetically. This grounds the code in the LLM semantics, so it understands what the IDs mean instead of just matching sequences. The final stage is another LoRa SFT on that adapter, training Qwen to retrieve problems with a predictive solve rate of 80 to 85%. After generation, we enforce like hard rules. For example, like skills not mastered, prerequisites not met, making sure there's no recent repeats of questions. Once that training stage is done, when you serve the model, Qwen-QRec proposes a few candidates of problems, and then the stage B evaluator that we had before is used to rank those candidates, and then you pick one with basically p-solve, or like the prediction probability that a student will solve that question is closest to 85%. And we reject everything if nothing lands between the band of 80 to 85%. Finally, the results. Qwen-QRec, my trained model, hit a recall at 16 of 95.7%. Opus 4.8, with a strong prompt in every question in context, got only a 16.7%, both scored on the independent evaluator. On a smaller eval, Qwen got 100%, both Opus 4.8 and GPT 5.6 each got 20%. Here's a concrete example. A student is doing some problems, got some wrong about rectangular prism volume, but they know how to do like arithmetic to like add, subtract, multiply, divide. Um, so we asked Qwen-QRec and a bunch of Claude as well as GPT Soul um, to recommend the student a problem in this scenario. Qwen-QRec gave the user a question about area, a step down from 3D volume, but definitely above arithmetic. Both Claude and GPT gave the user another question about arithmetic that the user has already shown proficiency in. It's too easy. And this is the problem that we want Qwen to solve. Finally, the next steps. The big one is improving and validating the knowledge tracing model we use to evaluate. It uses Howdot data, but the real test is with actual students to see if this really improves learning outcomes. This is my project, Qwen-QRec. If you're working with anything in the recommendation space or language modeling, feel free to reach out. I'm always interested in learning new things. Thanks for watching.